Second question we're going to do is question number 42, which reads as follows. Billiard ball A of mass ma equal 0.4 kilograms, moving with a speed va equal to 1.80 meters per second, strikes ball B, initially at rest, of mass 0.5 kilograms. As a result of the collision, ball A is deflected off at an angle of 30 degrees with a speed of 1.1 meters per second. Taking the x-axis to be the original direction of motion of ball A, write down the equations expressing the conservation of momentum. Solve these equations for VB and theta B of ball B. Do not assume the collision to be elastic. We haven't discussed elastic yet, so I'm glad we're going to assume this one is not elastic. And I'm going to change this question a little bit. It asks us to write down our components of x and y directions separately. I will talk to you about it as a two-dimensional problem, what that might look like, and then we'll do this as x and y. You should be able to solve these problems either using the component method or by using triangles. Okay, so writing my information down. Mass of ball A is 0.4 kilograms. I'm not going to bother with all the significant figures. We will make it so that our answer is in 2 or 3 significant figures. Okay, so here are our givens. Visually, this looks like the following. I've got a ball moving in this direction with its momentum. It hits ball B, which is more mass. We again assume that the center of masses collide directly and we're not dealing with spinning of any sort. This ball goes off. Momentum A prime goes off on an angle of 30 degrees to its original path. And you can assume that this ball will be going down this way. Just through your experience, I'm sure you would assume that anyhow. But initially, we can also notice that there's no y momentum here. Therefore, there should be no y momentum after. Therefore, the y component of A's momentum after must cancel with the y component of B's momentum after. So if I put this like this, there's my y momentum there, here's my y momentum there, they're equal to each other. I'm just ballparking the diagram, but I understand what equivalences have to take place. So if I was to solve this problem in x and y, I form two one-dimensional problems. If I was to solve this using a two-dimensional approach, then I would, as I did in the last problem, form a triangle and solve that triangle. That triangle would look like this. Here's my momentum A. Here's my momentum A prime. And then I have my momentum B prime. 3 momentums. the two momentums after, sum to or add tip to tail. I had to make that vector a little bit longer, that's why I had that there. Add tip to tail, these two add tip to tail to give us the original. What this tells us is that the sum of those two momentums equals that momentum. That's the conservation of momentum principle. Here's my 30 degrees. And if I was to solve this using a two-dimensional approach, though this might look like 90, I'm not to assume it. So I will have to use the cosine law. So I'm trying to find VB, momentum B. So momentum B squared, this one squared, equals this squared plus that squared, minus 2 times those together, cosine 30. That's the cosine law. And so I'll have to calculate out what these momentums are using my givens. And I can calculate this out, take the square root, and I find out what that momentum is. This is the two-dimensional approach. If I was to solve this as two one-dimensional problems, as the problem requests that I do, then I can solve it this way. I will notice that I have momentum A prime, I have momentum B prime, both of which have components of x and y. So if I wanted to solve this two one-dimensional, I write down the sum of my initial x momentums equals the sum of my final x momentums. And then I'll have momentum AX has to equal then the momentum of A prime x plus momentum of B prime x. To find out what this is easy. It's right there. They more or less give that to me. I find that product and I have it. These ones, on the other hand, involve trigonometry again. Notice that the momentum A prime x component has a cosine relationship. So the cosine of 30 equals momentum A prime x, you can see it right here, over momentum A prime. So we rearrange that equation, and we get that the momentum A prime x equals momentum A prime cosine of 30 degrees. And similarly, we find this value here. Now, the problem, of course, is I don't know what theta is, or in this case, I'll give it the notation of phi. I don't know what phi is, so I'll have to put cosine of phi in there. So in this equation, I know this. I know what momentum A prime is to give me the velocity. Its mass is the same, so I know what that is. I know all of this stuff. I know what its mass is. I don't know its velocity. And I don't know that. So I have two unknowns. So doing this substitution, if I need to solve for or get this by itself. Okay, so I know that I have V, B prime unknown and phi unknown in this equation that I've just formed by isolating my unknowns. So there's my x equation. Now what I'm going to do is I'm going to do the same thing for the y equation. I'm going to leave this right now, so I'm going to number it, equation 1. And now I'm going to do the y, approach the same. Notice that there is no y momentum to begin with, and that these two therefore cancel each other. I can jump directly to that, and I will in this case just because I don't want to take too much time doing this problem. So y initials equal the sum of the y finals. So 0 equals momentum A prime of y plus momentum B prime of y. And these two are, one's in one direction, one's in the other. So I could show the subtraction here, but it'll work itself out in giving one of them a negative velocity. So momentum A y prime equals momentum B y prime. Put that negative there. And doing as I did up above, I resolve this, and I notice this time I'm going to be dealing with the sine. So PA prime sine 30 equals momentum A y prime. And rho prime B times the sine of phi equals rho prime y of B. So I can make that substitution. Negative rho prime sine 30 degrees equals rho B prime sine of phi. Now we have two equations. This is now my second equation. And in these equations, I have two unknowns. Those two unknowns are the same for each of these equations, so I can use the methods of solving equations to solve it. Now I notice by looking at these equations, I have a cosine phi and a sine phi, and I further know that sine phi divided by cosine phi is tan phi. So what I'm going to do is I'm going to take equation 2 and divide that by equation 1. So you can look at your paper to see what that is, since you don't see that on the screen right now. And taking equation 2 then, which is right there, I'm going to divide that by equation 1, which looks like this. Notice now I'm putting in just rho A, because rho A is equal to rho X. And here's my equation. Don't make the mistake of turning this into a tangent right here. You can't do that division over a minus sign. So this whole denominator needs to be remaining underneath that whole numerator. But over here I do have a simplification I can make. Those two momentums cancel. They're equal to each other, and I get tan theta on the right-hand side. I wouldn't suggest normally writing this way, but to save some room, I will write this over here. So now this equals tangent of phi. And I know everything there is. So I can plug in all my values here and figure out what phi is. Solve for phi and take that back, substitute that in here or in the other equation, and solve for what the momentum of B will be. From there I can figure out what the velocity of B is by dividing by the mass.